So this is a talk on careers in astronomy, originally done for the Girl Scouts Heart of New Jersey in February 2020. Thank you very much, those of you who sent questions in advance. I'll incorporate answers into my talk. When I'm explicitly answering one of your questions, there's a question mark icon on the slide. So my first question to you is, what is the difference between scientists and engineers? For me, engineers build things and scientists learn about nature. That's the biggest distinction. So in practice, there's a continuum of individuals. There are some scientists who have more training in engineering and some engineers who have training as scientists, and there is overlap, but there's mostly two different populations and two different cultures. So NASA has a lot of both scientists and engineers, but they have more engineers than scientists because they're building things that go into space. If you want to have a really good mission, or for that matter, a telescope or any kind of scientific facility, you need to have both the scientists and the engineers working closely together. For example, several years ago, there was a mission called Deep Impact, which fired a projectile into a comet. And the engineers wanted to make the projectile out of a combination of materials that made sense to them, given what the probe was supposed to accomplish. But the astronomer said, oh, no, you cannot put copper wiring on this projectile, because the projectile is going to annihilate when it hits the comet. So we don't want any copper in the comet being confused with the copper from the wiring on the projectile. So you can't use copper wiring on this projectile. So in order to do a good job, in order to accomplish good things, you need to have both the engineers and the scientists working together. I'm a scientist. And there really is a different culture because I work at Caltech. JPL is not too far away. I'll let you figure out whether it's the scientists or the engineers who like having meetings at 8 a.m. Hint, most astronomers are night people. So are scientists and engineers creative people? Yes, scientists and engineers are very creative people. The popular conception is that scientists and engineers are not very creative people. But we have to be creative because we have to find creative solutions to very difficult problems. So for example, if you want to figure out, could life have existed on Mars now or ever? How would we find that out? So the scientists think about, well, as far as we know, life needs water. So the first thing we need to do is look for water now or in the past on Mars. So we would like to send a rolling robot geologist to Mars because so that it can drive all over the terrain and go where we want it to go. It needs to have tools that enable it to drill into rock. I really like it to vaporize parts of the rock so we can tell what the rocks are made of and take lots and lots of pictures so that we know where we are and where the water might have been. That way, we'll understand whether or not there was water on Mars, and from there we can try to understand whether or not there was life. So the engineers are like, really? You want to vaporize rock? Okay, for that energy requirement, we're going to have to use a small nuclear-powered car, and the best way we can think of to get it to Mars is to land it with a sky crane. So there's like a parachute with jets that help lower it slowly onto near the surface, and then release it on tethers down to the surface, set it gently down, and have that part fly away. The only way that you were going to come up with that is if you're creative. So creativity is absolutely critical to what we do. So in the context of the rover, the engineers' work was in getting the rover to Mars. I remember when the Mars rover first landed and the sky crane worked, there was lots of media coverage of the engineers, lots of interviews of the engineers. And every single interview that I heard, the reporter was like, so are you going to, what are you going to do with the rover now on Mars? And the engineers were like, I'm not working on it. The rover's there and it's working. I don't have anything left to do. I'm going to go work on building the submarine that's going to Europa. Because for them, the engineering is in getting the rover to Mars and making it work, right? The scientists, in contrast, did not have a lot of work to do in the beginning. The scientists were advising the engineers, but they didn't have a lot of work to do. Now that the rover is there and working, now they're busy because they're trying to use the rover to learn about nature. So in order to be a good astronomer, and for that matter, probably a good scientist in any field, you need to have a lot of tenacity. That means once you get your teeth into something, you don't want to let it go until it's done. Lots of creativity, as we were just talking about. Lots of attention to detail. I think probably most scientists are somewhere on some sort of OCD spectrum because you really have to pay attention to lots and lots of detail. You have to be willing to work really hard. You have to be really self-motivated. And you have to be able to communicate well in writing and in person. It doesn't matter if you're a genius scientist and you come up with something that's going to change the world. If you can't tell anybody about it, If you can't convince them to give you money to build it, that doesn't matter. It doesn't matter how brilliant your idea is. If you can't explain what you're doing, it doesn't get you anywhere. All scientists that I know, which admittedly is mostly astronomers and physicists, we do a lot of computer programming. And I don't mean like with Microsoft Word or Excel. I mean like Python, right? I mean actually getting into the guts of the program and writing your own programs. And of course, we do a lot of math and physics as well. And of course, astronomy, obviously. Depending on what kind of astronomer you want to be, you might also have a lot of overlap with chemistry or geology if you're interested in extraterrestrial life, even biology. Most astronomers have PhDs, so that means college plus graduate school. You will not pay for graduate school in the physical sciences, but you probably will pay for college. There's lots of scholarships available, of course, but just keep in mind that graduate students in the physical sciences usually get paid a stipend. It's not very much. I mean, it's like poverty line or below, but it pays the bills, right? And you're not racking up substantial amounts of debt in tuition. It turns out it doesn't matter so much where you go to college. You need to be able to learn, so you need a solid foundation, so you really need to be able to learn. So you need to find a place that's your tribe, that works for you, that people get along with. They provide you the support that you need. It provides you the opportunities that you want, and that could be big, small, urban, rural, rich, poor, huge, technical, liberal arts, whatever. As long as you're actually learning, that's what you need. You need to take as much physics and math and computer science as you possibly can get your hands on, depending on what kind of astronomer you want to be. You might also need chemistry or geology or biology too. And you need to get the astronomy in anywhere you can. Now, the reason I say that is because if I am, sitting on a plane, or something, and somebody wants to strike up a conversation, if I say that I'm an astronomer, usually they get very excited, which is good. But then a reasonable fraction of the time they want to talk about how they're a Leo, which is astrology, not astronomy. If I say that I'm a physicist or an astrophysicist, they go, oh, you must be really smart. And the conversation stops right there. So if you're trying to get a job, it's probably good to have the reaction from somebody who might hire you of, oh, you must be really smart. And if you have a degree in physics, that's the reaction you get. It turns out that real research is nothing at all like taking classes. There are many, many, many people who do really well in classes, but as soon as they get to graduate school and experience real research, they suddenly realize that they don't like it at all. Because real research is totally different. A problem set that you do in a classroom is going to have a finite set of problems and a finite set of answers, and a specific set of steps you're trying to get through to get the answer. Whereas real research is nothing like that. Real research is open-ended. You get to define the questions. You also need to define how you're going to get there. And you need to decide whether or not it's right when you get there. So totally different than problem sets. So there are several different kinds of astronomers. There are observers, like me. I use telescopes to observe things in many different wavelengths. And I try to interpret what I see. And that means that there is a lot of overlap depending on the kind of observer. They can have strong overlaps with computer science, such as things like machine learning, artificial intelligence, image reconstruction, that kind of thing. Theorists, in contrast, use physics to try to understand why we see what we see. So they're looking at the physics equations and trying to explain how that object is doing what we see it doing. Computer modelers are kind of hybrid observers and theorists because they have to understand the background physics in order to make a model, but then they make the model in the computer and they make suites of models and then observe the models and then try to compare that with the observations. So that too has a lot of overlap with computer science. There are instrument builders. They're the ones who build the telescopes and the cameras, and that of course has a strong overlap with engineering. There's also laboratory astrophysics. So in that context, they're trying to simulate conditions found elsewhere, but in the lab to try to explain what we see. So for example, if you observe a particular kind of element and you're not sure what it is, or a combination of emission lines, you're not sure what it is, you might go visit a laboratory astronomer, a laboratory astrophysicist, to try to understand, okay, well, I think it might be this molecule that's generating this emission line. So they can try to make that molecule in the lab and try to observe it to try to see if it is, in fact, generating the emission lines that you see. There are all sorts of astronomy-adjacent jobs. So we need writers to be media representatives, to explain concepts in writing to the public. And similarly, we need artists and animators because we need to make artist conceptions and we need to be able to explain difficult concepts for the press release. We've got lots of programmers here at IPAC, lots of actual credentialed software engineers. By that I mean like astronomers program a lot, but most of us don't have formal training in computer engineering or software engineering. We mostly are self-taught for the programming, but we have actual, like credentialed programmers that write the code for a lot of the stuff that we use here at the archive. We also need website designers and, of course, computer and administrative support staff. And then if there's a ground-based telescope, you also might have a telescope operator, and those telescope operators would actually sit at the telescope all night controlling the telescope. If you have a space-based telescope, you also need telescope operators, but that's a little different. In that case, you're planning the observations and scheduling and, participating in radiating that up to the spacecraft so that the spacecraft knows what to observe. So why am I doing astronomy? I've always loved astronomy. Ever since I was really little, that's pretty much all I ever wanted to be. I was completely mesmerized by anything NASA related, especially all the Voyager images from Jupiter and Saturn. I did fall off the wagon for a while in elementary school, middle school, high school, because I somehow, despite my parents' best efforts, bought into the idea that girls can't do math, which is obviously garbage. And I trust that things are different now than they were when I was little, and that I hope that none of you think that girls can't do math. So for me, I went to a public high school in Arlington, Virginia, in the Washington, D.C. area. I went to the College of William and Mary in Virginia, which is also a public school. I do have a bachelor's in physics. And then for graduate school, I went to the University of Chicago, where I have my master's and PhD in astronomy and astrophysics. William and Mary is a liberal arts college. And again, it's your choice of graduate school that makes way more difference than your college choice. Most astronomers have a couple-year postdoctoral position, at least one. So I was a postdoctoral scholar. I had a fellowship at the Jet Propulsion Laboratory not too far from here. And then I was hired here at IPAC at Caltech in 2002, and I've just been moving around jobs within IPAC since then. Just for context, if you can sort of map the various stages of an astronomer with sort of the medieval model of employment, right? So at grad school, you're an apprentice. You're closely tied to somebody while you're learning your trade. As a postdoc, you're a journeyman. So you have some independence, but you still have someone to go to get advice from. And then once you have a permanent job, then that's sort of analogous to a master in the Middle Ages. So what do I do specifically? So a professor is hired to do research and then teach undergrads and graduates, depending on the school. And also serve the university community. I am also paid to do research, but instead of teaching or serving the community in that way, I support telescopes and archives. So what that means is that I work for IRSA, which is the Infrared Science Archive, and that's NASA's home for lots and lots of infrared data. And so that means that I help write documentation, I test software, I help design software to try to make it easy for everybody to get access to data from IRSA, whether it's a summer student embarking on her very first research project or a emeritus professor who can barely read his email, and everybody in between. So we have to make the archives easy to use for everybody. Also, it turns out I run a program that helps teachers get into real research. That program's called NITARP. So I work with teachers to help them understand how science works. That also means that when I'm paid to do research, I do science. So that means that I travel to conferences, I write proposals, I serve on review committees, I go on observing runs, or I prepare observations for space observatories. When the data come back, I have to turn data into papers, and I have to reduce the data and interpret the data and then write the papers and then give talks to share what I've learned. Specifically, what I study is star formation, how stars like our sun form. So when I say young stars, I mean like less than 20 million old stars. That's old by human standards, but not by star standards. I also study how stars rotate with time, how the rotation rate of stars change with time, because you start out with a big cloud of gas and dust, and like a skater pulling in her arms, it should go faster and faster and faster and faster as it collapses. Turns out not all of them do, and then they slow down at different rates. So trying to understand that rotational history is something that I've been doing a lot of. So day to day, I spend a lot of time in front of my computer. I attend meetings just like this one online, but also in person. Because I'm an observer, I get data from telescopes all over the world and from various archives, and I try to understand how stars form and how the rotation rate changes based on the data that I have. I want to emphasize that no astronomer spends all of their time at a telescope, except for those people who are actually paid to operate the telescope. Most observers would be really lucky to get less than a week of observing time per year. And we pretty much never look through the telescope with our own eyes. We always have a camera at the back. Most professional telescopes don't even have an eyepiece attachment. You can't even if you wanted to, you couldn't. It takes a surprisingly long time to turn data into papers, years sometimes. I work at Caltech, but I travel all over the world because there are conferences and observatories all over the world, and astronomers in general travel a lot. And that's something that the community is trying to reckon with right now, because in the context of global warming, is it really appropriate for us to be racking up as many frequent flyer miles as we have been? So that's all things that are being discussed in the community right now. So scientists tend to work long hours. We tend to work more than 40 hours a week. When I was in high school, I didn't understand what that meant. At that point, the only jobs I'd had were like food service jobs. And let's be honest, those jobs are really, really hard. And for me, imagining doing that for much more than 40 hours a week just sounded terribly, terribly intimidating. But what I didn't understand is that when you love what you do, it doesn't really feel so much like work. So, I'm thinking about how to do things while I'm in the shower, or while I'm, driving home in the evening. I finally figure out how to solve the problem I've been playing with all day. So, there's a lot of work overlap with the rest of my life. So it doesn't really feel quite so much like work if you really love what you do. Also, when I was in high school, I loathed group projects with a fiery, fiery passion. I hated group projects. But as an adult, working with other smart, motivated people, they are so much fun. I really, really enjoy working in teams with really smart, motivated people, and it's so much better than it was when I was in elementary, middle, or high school. It's also true that my job is very flexible. That's the trade-off, right? I work a lot, but my hours are often irregular. I mean, to talk with you, I was in the office on a Sunday morning, right? So it is very flexible. And what that means is that my son, who is 11 and is a second-degree black belt in Taekwondo, he has Taekwondo practice at the end of the day, and I can leave early to take him there. Or he plays baseball, so I can leave early to make sure he gets to a game. Or to make a parent-teacher conference as far as that goes. So it is very, very flexible. And it is completely ridiculous that I get paid to have this much fun. So, that's the thing that just really keeps me going. It's just amazing. It's so much fun. So when I was your age, things I wish I had known besides the fact that girls can do math, I grew up in a house of predominantly women. I have two sisters, and my dad was the only man in the house, including the cat and the dog. So I didn't have a lot of experience with how men think or relate to the world. And I didn't understand that men interact with the world very, very differently than women do. And the best example that I've heard of this is, of course, that the women's gold medal winning soccer team has been, top of the world for a long time. But when that first gold medal team was assembling, they hired a man to be the coach of the women's soccer team. And he had never coached women before, but he'd coached men and done pretty well, which is why he'd gotten the job. And when he was coaching the men, he would have to yell and 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 yell to get the men to work. And the men would hear him, but they would think, oh, I'm doing fine. Everyone else needs to work harder, but I'm doing fine. So he took that same philosophy to the women's soccer team. And so he started yelling at their first practice. And all the women went, oh, I need to work so much harder. And they started really, really working harder. And the coach was like, whoa, okay, this is really different. I have to manage these women totally differently than I would manage a man. And that, now that I have a son, I have more insight into that than I've ever had before. Because, he plays baseball, and, he started when he was 8 or so. And when he was 10 or so, there's a team full of these incredibly overconfident little boys, right? And admittedly, they're playing on a baseball field that's not Major League Baseball size, it's smaller, but still, it's scaled for size, right? So if you're standing out in far right field, you better have a heck of an arm if you're going to make that to home plate. That throw to home plate. And it, as a professional Major League Baseball player, I watched Yasiel Puig, who is an amazing hitter, and whose arms the size of normal people's thighs. He's in far right field, and he threw a ball, and he made it to within about 5 feet of home plate. And that's a professional baseball player. So we've got these 10-year-old boys out in far right field trying to throw the ball to home plate. And the coach is standing there yelling at them, "If you are standing on grass, you will not make it to home plate. Hit the cutoff man, please." All these little boys were so confident in their abilities that they just knew they could do it, even though it was demonstrably obvious that they weren't doing it. Their confidence wasn't hit at all. And that's so different than how I interact with the world. And I wish I'd known that when I was your age, to understand that men and women just interact with the world totally differently. So last few slides I have are specific questions from you. Somebody wanted to know if there are even numbers of men and women in astronomy. No. About 30% of new PhDs are women. But the older you go, the worse it gets. Around the time that I was graduating with my PhD, it was about 25% women. And when you get up to even older, there's lower fraction of women. But interestingly, because men tend to die first, the fraction goes up again for seniors. There's a higher fraction of senior women astronomers than there are in earlier age bins. It's also true that those older women, they fought to get where they are. And so a man might retire and stop doing astronomy, but a woman who's reached retirement age, she's not going to go quietly. She's not going to stop being an astronomer very easily. So those two things mean that there's a higher fraction of women at the older bins than there are at the slightly younger than that bins. Is there discrimination? Yeah, because we're human, and that's what you have to deal with. Astronomy is relatively small. There's about 8,000 astronomers, professional astronomers in the U.S., and so that field is small enough compared to other scientific fields that we usually can adapt and change very, very quickly. So there's lots of examples of that, especially in modern astronomy. And there was someone who studied the political leanings of scientists, and apparently scientists as a whole are very liberal, but for that study at least, among the scientists that they talked to, the astronomers were the most liberal. And those two things means that there's been a lot of movements for social justice within the community in the last 10 years or so. So there are lots of people who are actively working to recognize where there's discrimination and to try to reduce it. Is it hard to get a job in astronomy? It depends. Depends on what you want to do. It's certainly true that not everyone who graduates with a PhD is going to end up a professor. So you have to be willing to be flexible and willing to see alternate career paths. If you have a degree in astrophysics, you can go do other things. You don't have to just stay and be a professor. Somebody asked, why can't I see so many stars at night? Because of light pollution, because there's lots of light emitted by cities. So you need to get out to a really dark place, and bonus points if you can find a very high and dry place, because then you can see more stars. Why do stars twinkle? Well, because we have an atmosphere, and we have weather, and the air is not smooth. It's very turbulent. And so that turbulence in the air makes the stars seem to shimmer, which is why they twinkle. For the record, stars twinkle and planets don't. That's because stars are true point sources, so like an infinitesimally small, bright point of light, but planets are measurably large, right? And so they don't twinkle as much. Somebody asked, what is the solar wind? Well, the sun is a giant ball of plasma, which is ionized gas. That means protons and electrons swimming around, not bound to each other in atoms. The sun also has a magnetic field, and so those charged particles can interact with the magnetic field. So they follow the magnetic field and they can drag the magnetic field. So the magnetic field is not smooth, and neither is the plasma itself. There's turbulence in there too. And because the sun is very hot, the charged particles at the outer edge of the atmosphere are so hot that gravity doesn't hold on to them anymore. So they leave and they follow the field lines as they go. That's the solar wind. So Earth's magnetic field helps protect us from the solar wind because it gives us sort of a magnetic shield. So when all of these particles are coming out from the solar wind and hitting the Earth, the atmosphere, or the magnetosphere directs the particles around the Earth. If you're an astronaut going to Mars, you're not going to have that protection. So that's something that NASA is actively working on. How do we protect astronauts going to Mars if there's a big solar flare and strong amounts of solar wind? So who was the first woman astronomer? I bet that the very first woman astronomer was someone who wanted to know when she was going to start bleeding. So she counted the days. There's several early calendars where there's hash marks like on a bone. Who would need to count 28 days? I think it was a woman. Could also have been that the first woman astronomer was someone who watched the stars every night to know when she needed to plant her seeds. It could have also been the woman who astronomer could have also been someone who knew that she was here and wanted to go there. And in order to figure out which direction there was, she noticed the position of the sun during the day and the stars at night. So I'm sure there were plenty of women astronomers well before there was light pollution, and you could live your life governed by those patterns and watch those patterns closely to learn what, how your life is interacting with those timescales. And, when do you need to plant? When are the rains coming? All those good things. Somebody asked, do constellations last forever? No, because the stars move and we move. Our system moves as well. So there's a really cool video from a mission called Gaia, which is mapping out the locations and motions of the stars. And so this is a picture of the nearby stars that make up the constellation Orion. And that's what it looks like, 500,000 years later. So there's some big changes there. If you go online, you can find this movie. It's really cool because you can watch all the stars moving around on their various trajectories, and you see nearby stars cruise through your field of view because Gaia, that's what Gaia studies. It knows the positions and motions of all of these stars. So there were lots of questions about cosmology. I am not a cosmologist, but I can try to answer them. How old is the universe? 13.6 billion years or thereabouts. How many galaxies are there? Probably 100, 200 billion. Is the universe expanding? Yes. Do the farther galaxies move faster than the galaxies that are close to us? Yes, because space is expanding. Why is there no center to the universe? Because space itself is expanding. So the best analogy I can think of is if you were like a two-dimensional being, very, very small, very flat being living on a surface of a balloon. As far as you're concerned, the balloon itself is space. And so if the balloon inflates, then all points in the balloon move away from all other points on the balloon. Now, it's true the balloon still has a center because that's not a very good analogy because it's expanding into the third dimension. So you have to sort of break your brain a little and think about how the space itself is expanding. It's not expanding into anything. Will the universe ever stop expanding? We don't know. How will the universe end? We don't know. How did it begin? We don't know. So thanks very much for all of your questions, and if you have any additional questions, you can feel free to email.